Okay, if you agree, we can start the webinar, and if someone join, welcome. So I'll welcome you all for today's webinar called Sustainable Agri-Food Systems, Circular Solutions for Water, Nutrients, and Bioresources in the Mediterranean. So thank you so much, all of you joining us today. Professor Giovanni is the chair. It's a great pleasure having such a project with you. Thanks, Eric, Stefano. So I hope this will be very successful and a good way to present such a topic. Before we start, I'd like just to go briefly through a couple of information about the journal, about the company, and then I will just invite Professor Giovanni to make some introductions about the webinar. MDPI is a pioneer in scholarly open access publishing, established in 1996 in Basel, in Switzerland, and has the mission to foster open science exchange in all forms across all the disciplines. So we have 422 very different and diverse open access journals, including 413 peer-reviewed journals, 9 conference journals, are supported by more than 1,500 academics, experts worldwide who share our mission, values, and commitment to providing high-quality services for our authors. The journal Sustainability is an international open access peer-reviewed journal that covers pretty much all the aspects of sustainability of human beings. So all the way from environment, culture, economy, and social sustainability. And it's been published semi-monthly online by MDPI. Regarding today's program, so we will have Professor Giovanni as the chair of this webinar to do some introduction, approximately 10 minutes. After the Professor Giovanni, we will invite Professor Erkan to join us in 10-20 to like in approximately 20 minutes. After Professor Erkan, we will invite Professor Eric to join us also for 20 minutes. And finally, Professor Francesco is going to share this third part, basically, of the webinar. And after all those presentations, we will invite you for Q&A section. So please feel free to ask any questions you might have. And finally, for the end, we will invite Professor Giovanni to close this meeting. When it comes to the relevant special issue related to this conference, you can check the sustainable fresh produce processing and byproducts utilization special issue on our website. And finally, that will be it. So Professor Giovanni comes from University of Napoli, Federico II in Italy, and I'd like to invite him now to just give us the brief introduction about himself and the webinar. Professor Giovanni, floor is yours.
Yes, thank you, Ms. Nikolic. I'm sharing my screen. I assume you can see it. So welcome everybody to this webinar organized in collaboration with the Sustainability Journal and in the framework of our MedInCircle project funded by in collaboration with the European Commission, but it is funded by the national states or the partners involved in the project. We have Napoli in Italy, then we have 2 partners in Turkey, the Istanbul Medeniyet University and Izmir Institute of Technology. We have 2 partners in France, the Institut de Physique du Globe de Paris and the University of Poitiers. And we have 1 partner in Egypt, that is the National Research Center. In this slide, you can see I make just a short introduction in the project before introducing the speakers of this webinar today. So here you can see the graphical abstract of the project. The core is the optimization of the circular management of water, nutrients, and bioresources. I try to use the pointer. Here you can see in green the agricultural field. So our idea is to treat the drainage water using nanofiltration and reverse osmosis, and then to treat the reject water together with the domestic wastewater in a wastewater treatment plant with the core in a biological system that is a moving bed membrane bioreactor and the UV disinfection. And the treated water is reused, recirculated in the field. And the sludge produced by the wastewater treatment plant is treated in an anaerobic digester, high solid anaerobic digester. And the digestate produced is also used in the field as biofertilizers. And also as biofertilizers, we are using the treated wastewater from an Agri-Food wastewater treatment plant, also aimed to produce biofertilizers that are biomass rich in carbon, nutrient, and phosphorus. And in this project, we have several working packages. And in the webinar of this morning, we will focus on 3 of these working packages that are working package 3, that is on the treatment of rural wastewater and drainage, agricultural drainage water. And in particular, Professor Erkan will focus on the reverse osmosis treatment. This nanofiltration and the reverse osmosis treatment here. And then we will move to working package 6, and Professor Eric will focus on the toxic metal, trace elements, pesticides, and other contaminants that we want to remove from the water and solid before using them in the field. And last but not least, Professor Di Capua will focus on working package 4, so on the high solid thermophilic anaerobic digestion to produce the digestate here that we will recirculate also in the field. So here you have the program. And I would like to soon give the floor to Professor Erkan to start with his presentation. Erkan, you have the floor.
Thank you very much. Now I am sharing my screen. Okay, thank you very much. I am Erkan Şahinkaya. I am from Istanbul Medeniyet University Bioengineering Department. And today I will talk about salinity and micropollutant removal from agricultural drainage water by nanofiltration and reverse osmosis process. So I will talk about especially nanofiltration and reverse osmosis processes in order to reuse agricultural drainage water and high salinity aquifer water. So as Professor Giovanni mentioned, our first aim is to treat agricultural drainage and aquifer water. So first of all, nanofiltration and reverse osmosis processes should be used in order to remove some micropollutant and remove salinity from both drainage water and aquifer, and then the recovered water can be reused for agricultural purposes. So in this slide shows the outline. First of all, I will give some brief introduction, which will be on the importance of water reuse in agriculture, then pesticides and salinity removal requirements in reuse applications, and then I will talk about materials and methods we have used. In the results and discussion part, first of all, I will talk about dead end and cross-flow filtration results, pesticide rejection performances at 2 different concentrations, high salinity rejection using membranes, and I will also give modeling results and lastly conclusion. So as you know, water scarcity is intensifying due to climate change, population growth, and agricultural intensification. And water reuse and recovery for irrigation purpose is a strategic need. Recovery and reuse ensure long-term water security in agriculture. So we have to focus on water reuse and recovery. And reuse of the drainage water is limited by residual agrochemicals, mainly pesticides. So the pesticides and salinity should be removed if we want to use them for irrigation purposes. And modern agriculture relies heavily on pesticides for productivity, but their presence in the drainage water poses both environmental risk and public hazards, of course. So the use of pesticide is increasing every day. For example, in 2014, the pesticide use was 2 million tons, but it increased to 3.7 million tons in 2022. So its usage increasing every day. And pesticide application is particularly high in developing countries, and lack of regulation and safe management practices increases contamination risks. So drainage water becomes a carrier of chemical pollutants. So when we look at the breakdown of pesticide usage, most of them is herbicides, around 53%, and then fungicide 22%, and the others little higher than 20%. So the objective of the study is to use 3 different membranes. 2 of them are nanofiltration and 1 of them is reverse osmosis membrane. So the aim is to use membrane processes in order to remove pesticides and salinity from agricultural drainage water and of course from groundwater. And if we look at the key elements of the study, we have used 2 different contamination scenarios. One is low pesticide concentration, which was selected as 0.5 micrograms per liter. And the high pesticide concentration was selected as 10 micrograms per liter. So 2 different contamination scenarios were studied using 3 different membranes. And membrane performance were assessed in terms of pesticide rejection efficiency and salt rejection capability. In addition to laboratory studies, we have used also simulation program in order to have a full scale system design with the flow rate of 100 meter cube per hour. Sorry. Okay. So for these purposes, we have selected 5 different pesticides: alachlor, atrazine, chlorfenvinphos, imidacloprid, and chlorsulfuron. So each pesticide has different molecular weights. If you look at the molecular weights, alachlor is the imidacloprid is the smallest pesticide, and chlorfenvinphos has the highest molecular weight. But in the membrane application, not only molecular weight, but also log KOV values, solubility, and other characteristics are also important. So the highest log KOV values belong to chlorfenvinphos, and the lowest one is imidacloprid and chlorsulfuron. So molecular weight and log KOV values are important parameters in the determining the rejection performance in the membrane processes. So this is the synthetic drainage water prepared in the laboratory. So these characteristics are based on our field experiences. We have taken some samples from both Şanlıurfa and İzmir in order to determine the characteristics of drainage water. And as I have mentioned, 3 different membranes have been used. 2 of them is nanofiltration and 1 of them is reverse osmosis. NF270 and NF90 membranes are nanofiltration membranes, and as you see, their molecular cutoff diameters are also listed in the table. And BW30 is the tightest membrane with the molecular weight cutoff diameter of only 100 daltons. And of course, when we look at the pure water permeability, the nanofiltration 280 is the one having the highest water permeability, because as you see, it's the loose membrane, and BW30 is the tightest membrane with the water permeability is only 4 LMH per bar. And here is the salt rejection performances. Of course, the best one is the BW30, but it has the lowest water permeability. So in the study, we have used dead-end and cross-filtration devices. In the dead-end filtration, as you guess, water is put to the holder of the membrane unit, and pressure is applied, and depending on the water recovery rate, concentrate stream remain in the holder. In the cross-flow filtration, we have used complete recycle mode. In this study, we have returned both permeate and concentrate to the feed stream. By this way, we have tried to see the steady state performance of the filtration processes. As I have mentioned, we have used 2 different contamination scenarios in the determination of pesticide rejection performance of drainage water. Also, we have used very high saline groundwater, and we try to remove salinity using reverse osmosis membrane, and we have tried to mimic Egyptian saline groundwater, because one of our colleagues is from Egyptian, and they have very high salinity groundwater and cannot be used for irrigation purposes, and we try to use membrane processes in order to remove salinity and make them applicable for irrigation purposes. So let's start with the pesticide rejection performance of nanofiltration and reverse osmosis. This is NF270 membrane performances is shown for the salinity removal. This is the filtration performances. So flux decreased to around 60 LMH under the 15 bar. As you see, salinity removal is only partial, and chloride concentration decreased from 600 to only 400 milligrams per liter. So I'm skipping a little faster for the time limitation. For the other NF membrane, which is nanofiltration 19 membrane, as you see, flux decreased little more to around 40 LMH after 2 hours later, but chlorine rejection is much better, and its concentration decreased to around 33 milligrams per liter. So BW30 is the tightest membrane, and the chloride concentration decreased up to 14 milligrams per liter. So its removal is highest in the reverse osmosis membrane, and flux decreased to 40 LMH during the filtration. Of course, this is the right one is the cross-flow filtration performance, and the left one shows the dead-end filtration performances. So dead-end filtration performance is important in the determination of concentrate stream, but cross-flow filtration is important for the permeate performances. So if you look at the dead-end filtration performance or dead-end filtration results, as you see, the concentrate chloride concentration in the concentrate stream increase up to, as you see, 5,000 milligrams per liter, because water recovery ratio is 80%, and the chloride concentration increase to very high levels, as you see. But in terms of the permeate quality, it may be better to concentrate on cross-flow filtration, because it gives the steady state conditions. But dead-end filtration shows how the membrane fluxes decreases with different water recovery rate, and how the concentrate stream characterization changes. So both cross-flow and dead-end filtration results should be considered together. Then we have started with modeling studies. The blue ones are our experimental results, and the orange one is the wave modeling performance. So as you see, modeling results are in good agreement with the laboratory studies, and then it shows that modeling can be safely used in the design of full-scale process. So we have designed full-scale process, and by this way, we have determined both concentrate and permeate stream. And as you see, the conductivity decreased from around 3,000 microsiemens per centimeter to around 80 microsiemens. And we have also designed and determined the required membrane area, required membrane modus, etc. So also we have determined the energy requirement for the process operation. And how about the pesticide rejection? So this result shows both, two different concentrations using dead-end filtration performance of different membranes. So this is 0.5 micrograms per liter performance, and this is the 10 micrograms per liter of performances. So as you see, as expected, reverse osmosis membrane, which was BW30, has the highest rejection performances. And interestingly, the rejection performance of chlorphenvin was with the nanofiltration, the loose nanofiltration is very low. Actually, we didn't reject it because it's a it's organophosphate pesticide and uncharged pesticide. So the nanofiltration membrane could not reject it at a low concentration. When we increase the concentration to 10 micrograms per liter, so the rejection performance, especially in NF90 and BW30, increased to over 95%. So this result also shows pesticide removal performance in the cross-flow filtration. We didn't as you see, the rejection performances in the cross-flow filtration is much higher. It's all at the low concentration, especially BW30 has always performance over 70%, and at the high concentration, NF90 and BW30 membranes gave over the 95% or 98% removal rejection performances for the reverse osmosis. So I will briefly mention about also the salinity rejection from groundwater. As I have mentioned, we have tried to mimic the Egyptian as high saline groundwater. So the conductivity is very close to is over than 8.5 millisiemens per centimeter. So we have only used NF90 and BW30 in order to see the performance of membrane processes in the removal of salinity. So as you see, salinity decrease from around 8.5 to less than 1 millisiemens per centimeter in the reverse osmosis process. And we decided that reverse osmosis process is much better. And also we have tried to model the process using, again, the wave process, wave modeling. And as you see, modeling results are in good agreement with our results. So as a conclusion, so we have evaluated 3 different membranes for the removal of pesticide and salinity. So it seems that membranes are good options in the removal of micropollutants. So especially if you use NF90 and reverse osmosis membranes, you can reject pesticide over 97% rejection performances. And also modeling results are in good agreement with the laboratory studies. So you can use modeling approach in order to design full-scale process. So it seems that the energy consumption for the agriculture drainage for 1 meter cube permeate water is only 0.5 kilowatt hour. So as a practical implications, membrane supports water reuse in the agriculture, and membrane processes are suitable for region with water scarcity and pesticide exposure. And So full-scale application can be reused in order to recover water for irrigation purpose. Thank you very much. So if you have any question.
Thank you very much, Erkan, for this very nice presentation with many results. So I think we have time for a few questions. You can raise your hand, or you can just open the microphone and ask the question.
Professor Giovanni, if you agree, we can leave the questions for the end. So let's make the flow of the presentation, and then finally at the end, it will be nice to have this Q&A section.
Okay.
Open. Yeah, thank you so much. Thank you.
I agree. So
Thanks.
we can thank you again, Erkan, and we can move to the next speaker, Professor Erik van Hulebusch. And as said, he will give a presentation on the comparative analysis of treated wastewater use regulations and environmental standards in the Euro-Mediterranean region. Erik, you have the floor.
Yes, thank you very much, Giovanni, for the introduction. It is all right. So thank you very much. Thank you everyone to attend this presentation. So my presentation will be a bit less applied than the previous one, but still very much connected. For this presentation, Jérôme and Leslie give me some help to prepare the slides. And so I will give an overview of the current situation about treated wastewater reuse in the MENA regions. First of all, I will give again some info about the importance of wastewater reuse with a focus on the Euro-Mediterranean region. Knowing that there is also growing needs for sustainable water management because of water scarcity. And then here we aim to compare the regulation and standard on treated wastewater. So I will only focus on the 4 countries which are involved in the MedInCircle project. But of course, there are many other applications like in Spain or Crete or any other place in the region that are also working on the treated wastewater reuse. So in the MENA regions, which includes the Southern Europe, so all this part of Europe, Northern Africa, and also Eastern Mediterranean area. So there are currently big challenges with drought. So here you have a map showing you a little bit the average precipitation anomalies so you are comparing here 2024 versus what happened in 1980 and 2010, and you see that the quantity of water which is received is decreasing in all the region. So all the countries are facing water scarcity mostly due to climate change, and then we have also issues with pollution, as it was previously introduced by Erkan. We know also that agriculture is a significant contributor to water stress in countries with high level. So you can see here that Northern African countries and Eastern countries are very much affected by water stress, mainly because of agricultural withdrawal from the resources. So treated wastewater reuse is a key solution or one of the key solutions to water challenges because it allows to answer issues of water scarcity. It comes as a complement to freshwater resources. It will also mitigate impact of climate change, and it will also address the needs of agriculture as well as urban needs. By reusing water, so we will reduce withdrawals from aquifers and rivers. That will also lower the discharge of water in natural environment. It will support irrigation, aquifer recharge, urban cleaning, industrial use, and even drinking water production could also be one of the challenges that we can address. However, if you look at the MENA region and in the world, you will see that reuse rates are fluctuating a lot, with Israel, which is able to reuse up to 90% of water. Singapore is also doing very well, and Spain. But in other countries, there is very low adoption in water reuse. And here there is a table that I extracted from this publication where you can see the wastewater reuse. Here it's for crop irrigation. And you can see that France and Egypt are not doing very well. But if you look at Israel, for instance, this is about 86%. Spain is about 22%, Tunisia 25%. So there is a big differences between countries regarding the wastewater reuse. Of course, when you are aiming to reuse water, you have to be aware about some issues, because we know that reclaimed wastewater contains contaminants, and then of course this may generate some risk, some health risk, but as well as environmental risk due to different exposure routes, as you can see here. And this may impact the health of people, the consumers that will be using water or food, but it may also impact the environment and also animal health. So this is just a scheme that shows you what could happen in case you are using a non-properly treated wastewater. Of course, it comes in there is a policy regarding this, and so policy is aiming to ensure safety and trust. So people should accept that water reuse is going to be done in a good way, so to preserve health and the environment, making people confident. To be clear and to make sure that we enforce the standards. And for that, in the European Union in 2020, there's water reuse regulation, which was enforced in 2020, and which has established minimum quality requirements for reusing water. This is mostly focusing on pathogens, suspended solids, and also BOD. And this regulation includes mandatory risk management procedures, require enhanced monitoring systems, and this applies only to agricultural irrigation, so for crops, for human or animal consumption. And the member states, so the EU member states, still have some flexibility in other use like industry, urban cleaning, aquifer research, and so on. So this regulation establish harmonized minimum water quality and monitoring requirements all across EU member states. It promotes safe reuse of treated urban wastewater in agriculture, and this is also supporting circular economy and enhanced water resource sustainability. Of course, there is risk management and permitting together with mandatory water reuse risk management plans, permits which are required for the production and supply of reclaimed water. Regular monitoring and compliance checks should be done. And of course, there should be transparent communication to the public through providing information on water reuse projects. The benefits is, of course, to mitigate water scarcity, which affects at least 11% of the European countries. Potential to increase water reuse sixfold compared to the current situation, reduce reliance on freshwater resources, and also enhance nutrient recovery and reduce fertilizer use. So this is a table where you can see that depending on the reclaimed water quality class, which moves from A, B, C, and D, depending on the class, you have different categories from where you can use it. So if you are A, you are able to use the water for crops that could be so for irrigation of fields, for crops consumption. Then if you are looking at class D, this is going to be industrial, energy, and seed crops applications. So depending on different classes, you will have to check the presence of pathogens with contamination indicators with E. coli, BOD5, which is one of the new quality parameter, suspended solid turbidity, and then there are a few other parameters which are used depending on the situation where, for instance, Legionella is going to be checked where there is a risk of aerosolization, or in some cases, if you are looking at nematodes, then it will be checked in case you are using water for irrigation of pastures and forage. So these are the parameters, which are also the frequency of the quality check parameter. Then if we go to France, so of course, as being a EU state member, the national regulation aligns with the EU directives. There has been very recently several updates. About in 1 year, we got like 8 new legal texts, which include the decree of August 2023, which also simplify the authorization procedure. Of course, one of the hurdles is to get authorization to reuse water, and this has been seen for a very long time as a difficult point. And then also expanding permissible uses of treated water. So that's also something which has been shown, demonstrated as a bottleneck for water reuse in France. Of course, the quality qualification is about the same as the EU directives. And the national target is to initiate by 2027 about 1,000 reuse projects, and to increase the reuse rate of treated water to 10% in 2030, and which is much higher than the current one, which is 1%. If we look in Italy, Italy has been one of the leader in wastewater reuse. So they are especially for agriculture. So they have a ministerial decree from 23, where which regulate the uses, especially in agriculture. They have local authorities that have flexibility to issue permits, which encourage project development. Many projects have been focused in the south of Italy, in Sicily, for instance, and where they have issues with drought conditions. And of course, as Italy is being a EU member, they have to comply with the EU regulation. And so they have to comply by 2023, which they have done. In Turkey, there is 2 regulations enforced. So the regulation on water pollution control and another one on wastewater treatment plants technical procedure communique. So they define again permit reuse purposes, they set water quality standards according to the use, and they specify the required treatment level to reach this target. And of course, they have also goals. So reuse target by 2023 was 5%, and by 2030 is 15%. Municipalities have responsibility to conduct feasibility and profitability studies. And currently, the reuse is estimated between 1 to 4%, which is a bit below to what was expected in 2023. In Egypt, so there are 2 legal documents that has been published in 2005 and 2012. So the current practice is that nearly 50% of treated water is reused, but significant part of it is being as indirect reuse, which means this is mixed with Nile water, and the reuse occur both in planned and unplanned conditions. So this is one of the particular conditions in Egypt, that there is not fully controlled reuse of wastewater. That is why you have inconsistent reporting on the reuse rates. We know that indirect reuse complicates the measurements, and there is a need for clarified and standardized monitoring systems. So then there is an issue here to really control what is happening in the country. However, there are a 2030 vision plan where it is planned to invest nearly $300 million by 2030. There will be also regulatory expansion beyond agricultural use, like groundwater discharge, dust control, firefighting. And it is anticipated that there will be a framework that will be upgraded by 2030. So just to sum up, the core concept of regulation is to ensure water quality thresholds. So all water reuse regulation define quality standards, which are often structured into classes associated with specific uses. And then there are two types of systems: single class systems, one standard for many use, or multi-class system, meaning different standards per use of the water that you are going to use. In terms of water quality parameter, the primary focus is health risk. So basically, pathogens, viruses, bacteria, parasites. This is really the main target. The secondary focus is the environmental impact, where you can include their heavy metals, organic micropollutants. And this last one is related to salinity, and this is not very much addressed at this stage, but in the regulation, I mean. But as you have seen from the previous presentation, this is addressed in research. So in EU, we have up to 4 water quality classes, which are based on crop type in irrigation method. And then for the European reuse, this is often aligned on the highest agricultural class. And in some countries, you have integrated approaches, like in Cyprus, Turkey, and Israel. And very often, the water quality classes are linked to treatment technologies, and you have seen some examples in the previous presentation how we can address this issue. The World Health Organization guidelines is very much used as a baseline to recommend treatment options for each reuse purposes. So this is a table which summarizes what we have in European countries with different classes, with the targets and the quality, and also the irrigation method here. And then we have the data from Turkey and some data from Egypt. So I'm not going to comment because time is running, but you can see that very often we have different classes and different parameters, which may vary from one country to another. But basically, the idea is somehow very similar. So in this regulation, pathogens and microbes is very much addressed. And then here you see the mitigation strategies that we can look at. Pesticides, organic contaminants, heavy metals, and salinity can be addressed by using different strategies, which is not only involving advanced technologies, but we have also nitrate-based solutions that are also considered. So that's something which is also important to consider. And then to conclude on my presentation, first, there is a need for harmonizing standards across all the region. So this is happening. This is gradually happening for water. Of course, when you are dealing with water quality or reuse water quality, you are also trying to address issues on soil contamination, on food quality. So this is done to reduce transboundary risk. Of course, if you get food from one country which is not aligned with the regulation of Europe, for instance, it may generate some risk for selling the food in Europe, for instance, and the other way around. So we have to adapt European benchmark to local context, ensuring trade facilitation and hence public health protection. There is also some work to be done on preventing pollution at the source, so phasing out hazardous substances. So here I mentioned about PFAS, which is one critical point, but we have also persistent organic pollutants, and this has to be done through regional coordination. And then there should also be some focus on proactive measures to prevent pollution and anticipate regulatory change. That is why we got in Europe the revised urban wastewater treatment directives, which was published last year, and where you have now a quaternary treatment step where we are addressing issues with antibiotic resistance, organic micropollutants, metals, and also removal of pathogens, which will be able to produce better quality water for reuse. And also promoting sustainable agricultural practices, so agroecology and responsible use of agricultural chemicals. As you have seen from the previous presentation, if you get drainage water or any agricultural wastewater or industrial wastewater, you may have pesticides. So if you promote more responsible practices, then you may limit the amount of pesticides there. And then there could be also a strict control on organic amendments, so compost and sludge, which also needs to be considered, which is somehow a bit connected to water reuse. That means that we have to look at enhancing monitoring and research capacity, which is done basically in the PRIMA framework. So these big ERANET projects, which involve different countries from the MENAT regions, and that we also do in MedInCircle project. So improving environmental monitoring, looking at emerging contaminants. So we speak about microplastics, but we will also speak about PFAS, perfluorinated compounds. There should be also supporting local research to better understand the local impact of contamination. So that we need to strengthen collaboration between countries. We have to support innovation and technology transfer, so promote adoption of proven treatment technologies, ozonation, bioremediation, membrane technologies. So this can be done through a regional program, which include PRIMA programs, but Horizon Europe as well, to accelerate dissemination of innovative solutions. And the way forward is that, for the future of Mediterranean environmental health, it relies on collaborative efforts and scientific advancements, and also harmonization and cooperation of key which are the key for improving food safety and protecting shared ecosystems. So with this, I would like to thank you with your attention, and I would like to highlight there is currently a cost action where many countries could contribute, which is called mainstreaming water reuse into the circular economy paradigm, which is water for reuse. And this cost action is meant as networking for improving to a better understanding water reuse and making sure that we can generate good quality water and understand how we can limit contamination. With this, I would like to thank you very much.
Thank you very much, Eric, for this interesting overview on wastewater reuse legislation. So in view of time, we can move to the last speaker. Professor Di Capua, you have the floor.
So with my presentation, I'm going to talk you about the process of high solid anaerobic digestion, focusing mainly on sewage sludge, but also on various organic waste. And we will see together the challenges, but especially the opportunities that this process can give us for the valorization of organic waste. So we are all familiar with the concept of circular economy. Based on this concept, the organic waste should be reintroduced into the production cycle, and we can do that with a variety of organic waste. For instance, food waste can be collected, processed through anaerobic digestion, used to produce biogas and digestate. The biogas can produce energy that we can use in our productive activities to generate other food, to clean wastewater, for instance, generate sewage sludge, and the digestate can be applied on the field to produce food, which then produce other waste that can be reintroduced into into the cycle. So we have this closed loop, okay, that can be used to valorize the organic waste that we have. We can produce a lot of organic waste with our activities. Among these, we have the sewage sludge that is produced in wastewater treatment plants. We have lots of agricultural residues. So we have animal manure, and of course, we have food waste. All these organic waste are highly available. We can find them almost everywhere and are continuously generated. They have also some cons like seasonal variation. So in some time of the year, we can find more of this waste than in other time. They can be quite heterogeneous. Let's think to the lignocellulosic materials. And also, of course, the storage and transportation of these substrates to the valorization hub might be challenging because of their availability, their emissions in terms of odors, for instance. So this is something that we should take into account. How can we process this waste? There are several ways. We can have a physical treatment resulting in the production of solid fuel. We think to lignocellulosic materials that can be crushed, ground, dried, pelletized to produce solid fuel. Then we can process them through thermochemical treatments such as combustion, gasification, torrefaction, pyrolysis, hydrothermal liquefaction, or carbonization. And with all this treatment, we can produce several streams, gaseous, solid, and liquid streams, such as the biochar, the syngas, the bio-oil, and so on. And also we can treat these organic waste through biological treatments such as fermentation or anaerobic digestions that produce the biogas. So overall, with all these processes, we produce energy and materials, and the main end product are transportation fuel, power and electricity, and commodities and fine chemicals. Let's focus on the anaerobic digestion process, how this works. This is a multi-step process that starts with hydrolysis of macromolecules, such as carbohydrates, protein, and lipids, to produce smaller compounds, sugar, amino acids, and fatty acids that can be fermented into even smaller molecules, such as volatile fatty acids, alcohols like ethanol, and other carboxylic acids like non-volatile fatty acid like lactic or succinic acid, for instance. From these compounds, we can have an acetogenic phase to produce acetic acid that can then be converted into biomethane. Okay, so the main product of anaerobic digestion. And the same can be produced through hydrogen and CO2 with the process known as hydrogenotrophic methanogenesis. So in the end, we mainly produce biogas as the gaseous stream. We could also think to cut the digestion process to the fermentative step, produce volatile fatty acids, and use these for producing some platform chemicals, fragrances, preservatives through physical separation of the single volatile fatty acids. We can convert them into esters and polymers for the production, for instance, of plastics. We could do some biological conversion, producing biopolymers or longer carboxylic acids, like the medium chain fatty acids that can be used in industries. And we can also produce hydrogen and biogas through completing anaerobic digestion for the production, for instance, of electricity, and also obtain a digestate that can be used as a fertilizer. For instance, this is one study that we performed in our group for the valorization of food waste through acetogenic fermentation that was optimized to produce electron donors and electron acceptors for the chain elongation process to produce in the end caproic acid, which is a medium-chain fatty acid that can be used as a platform chemical in pharmaceutical or cosmetic industry. But let's focus on the complete anaerobic digestion pathway. In this case, we have two main outputs. The biogas that can be used to produce electricity, heat, as a vehicle fuel and can be upgraded to biomethane and injected in the gas grid. And then we have a solid residue that is the digestate that has a very good composition in terms of organic matter and nutrients, and therefore can be used as organic fertilizers, as soil amendment, or also for the production of building materials or as animal bedding, of course. For instance, you can see here on the right, this is an example of how the digestate is injected in the agricultural land through this truck that, with anchors that go deep into the land, inject the digestate about 15 or 30 centimeters below the land surface to mix it with the land and improve the fertilizing potential of the land. What happens in conventional municipal wastewater treatment plants? Here we have the anaerobic digestion process that produces biogas and digestate, as I said. And in the digestate, we have about 27–30% of the influent COD that we have in the wastewater. This process is performed at a TS content between 2 and 5% in municipal wastewater treatment plant. Therefore, this process is also known as a low-solid anaerobic digestion. This anaerobic digestion process is not always foreseen in wastewater treatment plants because of many reasons: limited space, high investment cost, or because an aerobic treatment has been planned at the beginning. Also, sometimes anaerobic digestion is not efficient because it is performed at ambient temperature, and we know that it must be performed at least at mesophilic temperature to have a significant biogas production. And sometimes for the way with which the plant is operated, we have small sludge production, and therefore also the biogas production is quite low. So the anaerobic digestion is not efficient. So there is another way to operate anaerobic digestion, and this is to centralize the process by transferring all the produced sewage sludge into some centralized plants which perform anaerobic digestion at high solid content. This because the sludge is first dewatered to reduce the volume and to make transportation more convenient, and then is transferred to these big sludge processing hubs that perform anaerobic digestion at high solid content, usually is always about 6%. And will produce electricity, can upgrade the sludge to biomethane, and produce the digestate that must be applied on land. This is a must for the centralized plant because they produce a huge amount of digestate, and it must be applied on land in order to dispose of it, but I would say in order to valorize the sludge. In general, when we focus on the difference between low solid and high solid anaerobic digestion for organic substrates, I would say, except sewage sludge, we can say that we have low solid anaerobic digestion when the total solid content is below 10%, while when we are in the range between 10 and 40%, we can talk about high solid anaerobic digestion. This is true especially for lignocellulosic materials, food waste, and all these kind of organic substrates. So one disadvantage of high solid anaerobic digestion might be a lower volatile solid reduction, because the organic matter is a little bit less accessible with the high solid process as there is less water. So the biomass, the microorganisms find it a little bit more difficult to find the organic matter and to convert the organic matter into other substrates and into biogas. On the other side, we can process more organic matter at the same time because the initial TS content is higher. So if we maintain the same hydraulic retention time in the digester, we can have a higher organic loading rates. Another disadvantage is that when we work with substrates with high solid content, they are a little bit more difficult to be moved. So we have to use special pumping equipment to move these substrates that is also more expensive. So this is additional cost for the plant. But we have also a lot of advantage. For instance, we can make smaller digesters if we want to use the same organic loading rates. We have less water, and this means that we have to use less energy for heating the digesters. Also, the digestate that we produce do not need dewatering because it is already dewatered. There is already very little water in it, so it can be disposed or better applied on land directly. And also the quality is generally better because the solid anaerobic digestion is often performed at thermophilic temperature and has a better nutrient content and also better hygienic properties. So in the end, if we focus on the high solid anaerobic digestion of sewage sludge, we have many opportunities such as a higher biogas production, lower cost for transportation of the digestate because it has to be applied on land in the close to the plant. We can build smaller digesters using the same organic loading rate, and we produce digestate that is very good in terms of nutrient and hygienic properties. The challenges might be slower hydrolysis because there is less water, and also there is the presence of flocculants in this sludge that makes stronger aggregates. So it's more difficult for the bacteria to access the organic matter. The viscosity is quite high, so we have a difficult rheology, so the pumping is quite difficult. We may produce more inhibitors during the process, such as ammonia and hydrogen sulfide, and therefore also the purification of biogas might be more challenging. As I said, the zoohydrolysis depends on the difficulty in breaking the cell membrane, higher APS concentration, and the presence of floc aggregates in the sludge. The high viscosity depends on the floc aggregates and on the low water content in the sludge. The process inhibition is due to the high ammonia production, high hydrogen sulfide production, and we have kind of a dirtier biogas compared to the conventional digestions that is due to also the presence of siloxanes, so with silica in it, and volatile organic compounds that also may cause damage to metallic and plastic installations in the plant. Also, if we perform that at thermophilic temperature, like it is usually performed for high solid anaerobic digestion, we can have higher biogas production, produce more hygienic digestate because of the higher temperature, but also because we have higher free ammonia levels that are more effective in inhibiting pathogens such as Salmonella. And we have a microbiome that can withstand higher levels of free ammonia. We have to be careful when we introduce a sudden increase in the nitrogen ratio because in the nitrogen content of the feedstock, because working at higher temperature makes the ratio of free ammonia to total ammonia higher. So when we introduce some nitrogen in the system, this is mostly transformed into free ammonia that is more inhibitory for the bacteria, especially for the methanogens. And also, we know that thermophilic operation is more expensive because we have to provide more energy for heating and also to make a better insulation of the digesters to try to keep the heat inside the digester. There is a process, a specific digestion process called co-digestion, in which we process not only one substrate, like could be sewage sludge or food waste, but we couple different substrate together, we process them together in the same digester, and these can be advantageous compared to the so-called monodigestion, so with one single substrate. Why? Because with co-digestion we can enhance the production of biogas and can enhance the solid reduction because of many advantages. For instance, ammonia inhibition can be alleviated because by mixing different substrates, we can have a more balanced carbon to nitrogen ratio inside the digester. At the same time, we can reduce the inhibition of other substrates by selecting specific feedstock to be co-digested. We have a more resilient and robust microbial population because it is more diversified. We can optimize the mixing ratio among the feedstock in order to obtain a better digestion process. We can reduce sludge viscosity because if we have a feedstock that is very viscous, has a very high viscosity, we can mix it with a less viscous substrate and enhance the mixing inside the digester. And also the digestate quality can be improved because we can process different substrates together in order to have a digestate that is more balanced in terms of nutrients, so in terms of ratio of nitrogen, phosphorus, and potassium, for instance, and therefore has a better fertilizing properties. The main challenges of the co-digestion is the availability and accessibility of different substrates, because of course we need to collect different substrate in the same place, and this is not always easy because they are not generated in the same place, so we have to collect from different places, transport them to the same place, and process them together in the right amount, in the right ratio. So this is might be one challenging thing to have for co-digestion. So regarding our MedInCircle project, there is a specific work package focusing on the high solid thermophilic anaerobic digestion of different organic substrates, including agri-food solid waste and sewage sludge generated by the innovative municipal wastewater treatment plant system that was described before by Professor Shahin Kaya. We have different tasks for this work package. I will focus briefly on the first two tasks. So in the task one, we have performed a literature survey to select the most common and available organic substrates in two countries that were mainly involved in this work package, that are Italy and Turkey. And we defined what was the annual amount produced in each country to understand what was the availability of these substrates for co-digestion. We also made a characterization in terms of physical chemical properties of these substrates to understand what was their nutrient content, their biomethane potential, their heavy metal content also, for instance, to know them better and decide what substrates to co-digest. We made also a plan for our experiments, calculating what could be the total solid content of different co-digestion mixtures and what could be the expected biomethane potential from the co-digestion reactor. And then we selected the different substrates, both for Italy and for Turkey. In Italy, we selected the cheese whey, buffalo manure, the watered sewage sludge, the liquid fraction of the organic fraction of municipal solid waste, and the piggery slurry. While for Turkey, we focused more on lignocellulosic materials. So we selected grapevine pruning, olive pomace, wheat straw, grape pomace, sugar beet leaves, and also the liquid fraction of the organic municipal solid waste. We made a characterization of all these substrates. As you can see, these are the substrates that were collected in Italy. They were collected mainly in Campania region, where Unina is located. There are very typical substrates like buffalo manure, that is very typical activity, agricultural activity in Campania region, but also we collected something from northern Italy, for instance. So these are representative of the whole country. We made a characterization in terms of solid content, in terms of pH, in terms of total and soluble COD, and the same we did in Turkey for the substrates that were selected there. And then we selected potential combinations of these substrates that we thought that could improve the anaerobic digestion process of the single substrates. So we defined some co-digestion experiments and compared with the monodigestion of the single substrates. This was done for the substrate collected in Italy and for the substrate collected in Turkey. These are the experimental conditions. So we worked at thermophilic temperature. The total solid content was in the range of 9.5, 11.5, more or less, so in the range of the high solid anaerobic digestion. Inoculum to substrate was 2:1. We used 50% VS from one substrate and 50% VS from another substrates, and the inoculum was for instance, for Italy, was digested from buffalo manure mixed with the municipal wastewater sludge adapted at thermophilic conditions. These are the conditions for Turkey that are basically almost the same. This is an example of our experimental setup. So the water bath at thermophilic temperature. This is the system that we used for monitoring the biogas production and the biomethane production from our reactors. And these are some of our first results. These are the biomethane production curves that we obtained in Turkey, so with the substrates selected in Turkey. So on the left, you can see the co-digestion curves related to the biomethane production. On the right, the monodigestion curves. In general, as you can see, higher biomethane production was observed with the co-digestion of different substrate mixtures that were selected. Especially when we utilized the organic fraction of municipal solid waste in terms of liquid fraction, we could increase quite a lot the biomethane potential of some lignocellulosic materials like grapevine pruning and wheat straw. Because the liquid fraction of organic municipal solid waste has a very high biomethane potential. So it can be used to improve the overall biogas production from this substrate. But it's interesting to see that also when we combine together some substrates like olive pomace and sugar beet leaves that have a smaller biomethane potential, when we combine them together, we can get a curve that is higher than the two of them of the single substrate. So this shows that yes.
You should move to the conclusions.
Yes, it's finished. So these are the results shown in Napoli that basically shows also that co-digestion can actually improve the biomethane potential of some substrates. Of course, when we focused on Piggery slurry and the liquid fraction, we got higher biomethane potential because they are supposed to have a higher biomethane potential. And we will focus on further analysis to characterize the digestate, and the next step will also include the continuous bioreactor operation, comparison with commercial fertilizers, and agronomic test with the digestate produced from the co-digestion reactors. That's all. Thank you very much.
Thank you very much, Francesco, for this nice presentation on the advantages of the high solid thermophilic anaerobic digestion, and the preliminary results you obtained both in Italy and in Turkey in the framework of the MedInCircle project. So we have now time for the discussion. So I would like to open the floor for discussion. You can ask questions to the three speakers of this morning.
I'd like to thank you all for today's session, and I'd like to encourage all the participants, if they don't feel like talking, they can always leave the message in Q&A box, and our speakers and chair will answer all of your questions. So please feel free to send the questions.
Okay, do you see my name? My hand? Great. Okay. Yeah, it's me. I don't see myself actually. I don't know why.
Yeah.
We
see you.
We see you.
Okay.
We see you.
So thanks to all the speakers for the very interesting presentations. So at the moment I have a question for Professor Shahin Kaya, for Erkan. So Erkan, thanks for sharing with us your results about the removal of pesticides with membrane technologies. One question I was thinking is about the possible influence of salinity on the removal of pesticides from this water, if you evaluated that, and if you can bit more discuss about this issue that you might face during treatment of this particular water with a high concentration of pesticides.
Okay. Thank you very much for your question. Actually, the impact of salinity on the removal of pesticide completely depends on the membrane you have selected. For the nanofiltration membranes, especially for the loose membrane NF270, the main removal mechanism is electrostatic repulsion, because if you look at the molecular cutoff diameter and molecular size of the pesticide, it seems that all the pesticides can pass through the nanofiltration membranes. However, we can see some removal efficiency or rejection performance. The rejection, the mechanism behind the rejection of nanofiltration membrane is sometimes absorption of the pesticides on membrane, but mainly is the electrostatic repulsion of the membrane. So if the salinity change the charge of the membrane and also charge of the pollutants, the removal efficiency can be negatively or sometimes positively impacted. But in terms of reverse osmosis process, the presence of salinity may not have significant impact, because the molecular cutoff diameter of a reverse osmosis membrane is much smaller than the pesticide we have selected. So the molecular cutoff diameter is only 100, so it may reject almost all the pesticide based on their molecular size. By the way, of course, we can reject the pesticide using reverse osmosis membranes, but the more important thing is the concentrate stream. For example, in our test, we have observed that when the concentration is 10 micrograms per liter, the permeate concentration of the pesticides are always very close to 0.5 micrograms per liter in the reverse osmosis permeate. But in the concentrate streams, their concentration increase above the 30 micrograms per liter, so which is much more important. So our project, the PRIMA project, actually is based on this fact. So we are also using moving bed membrane bioreactors in order to eliminate or in order to decrease health effect or environmental impacts of this reverse osmosis concentrate using some novel both membrane and bio-based technologies, which may be one of the core of the PRIMA project. I didn't mention these processes here because I have mainly focused on reverse osmosis removal or rejection performances.
Okay, thanks, Erkan.
You're welcome.
Any further question? Silvio.
Hello, hi everyone. I want to thank you all for the nice presentations. I have a question for Professor Di Capo about his presentation concerning high solid thermophilic anaerobic digestion. So actually, I was wondering, do you have or is there any evidence about the fact that having so little liquid digestate content, so low water content, you also have a different effect in terms of the up concentration of any potential contaminants in the liquid phase. So, I mean, when you deal with agricultural waste, you might have pesticides, you might have antibiotics, and so on. So, how does this different configuration in the high solid anaerobic digestion affect their distribution in the liquid phase? And if in your project you're going also to assess this aspect. Thank you.
Thank you very much, Silvio, for your nice, interesting question. Actually, I mean, you are right. Of course, when you have a higher total solid content, you will end up with a higher concentration of everything, basically. So if you have more contaminants in your feedstock, then if you keep more solid in the digester, you will have a higher concentration of maybe pesticides, maybe antibiotics. But at least in my experience, I did not focus much on this kind of contaminants. I focused more on some inhibitors such as ammonia and hydrogen sulfide. This depends a lot on the initial substrates that you have. So there are substrates that are quite moderate, let's say, or even poor of these compounds. So even if you increase the total solid content, yeah, you will have higher concentration of sulfur and nitrogen in your system, but this should not affect much your system. Of course, this depends also on the conditions that you are working with. For instance, if you have quite high nitrogen concentration and you work at thermophilic temperature, you need to be careful because your levels of free ammonia in the system can be quite high and can inhibit the system. Or if you have a high total solid content, the mixing in the digester might be more challenging and you might have accumulation of acids in your system. So you can have spot acidification in your system, and this also is dangerous for the digestion process. So the mixing should be very good. That can alleviate the accumulation of toxic compound in some portions of the digesters, and co-digestion can help in this to alleviate the potential inhibitory effect of some specific compound. We will in the project monitor the content of pesticides, especially pesticides and pharmaceuticals in the digestate that are representative also of what was happening in the digester. So we will see how much of this compound we have in the feedstock and how much of these compounds will end up in the digestate, and in this way we can also have an idea of the biodegradation of these compounds during the anaerobic digestion process.
Great. Thank you.
Thank you. We have still time for a few questions more. I'm checking also the chat box. Okay, I see Anna Chiara.
Good morning, everyone. So I wanted to ask all three presenters, actually, what are their expectations regarding their most important environmental impacts expected by the technologies that they're trying to develop? Because, of course, the aim is to improve circularity and trying to reduce the impact of traditional technologies, but what kind of issues do you expect with the technologies that you're proposing? And also, how do you plan to address these issues? Thank you.
If you want, I can start. Giovanni.
Or shall I maybe introduce the regulation aspects? I don't know. Maybe I can take over here. So as you have seen from my presentation, I mostly addressed issues with pathogens, the suspended solids, looking at also BOD. So this is what the regulation is requested at the moment. I also mentioned that the new wastewater treatment framework is pushing all wastewater treatment plants to move to the quaternary treatment. So where we have to decrease to make sure that the concentration of contaminants is going to be lowered very much. So that's so there will be quite some work done on the quality of water that we can further reuse, as mentioned. And of course, different type of technology will play a big role. And I see that the membrane technology is going to be one of the main technology that will contribute to lower the concentration of contaminants. So that's and this is somehow considered in the regulation as well.
Yeah, I can also mention about the membrane technology. So we have run nanofiltration and reverse osmosis processes in order to remove both salinity and pesticides from drainage water and groundwater. So the concentration of pesticides in the drainage water are actually very low, but it's of course its health impact and environmental impacts are very high. So its concentration are in micrograms or sometimes at nanogram levels. So the only one of the best technologies in order to remove these low concentrations are the use of membranes. So the membrane technologies can be safely used to remove pesticide and salinity from both groundwater and agriculture drainage water, especially for the irrigation. But the problem, the challenges of using these technologies are the cost of the processes, of course, because reverse osmosis and nanofiltration processes are commonly used, especially for desalinating seawater for the production of drinking water, etc. So we have experiences in the use of reverse osmosis processes both for seawater, groundwater, and wastewater, of course. But as I have mentioned, the problem is the cost of the processes. But if you consider that water scarcity is the main problem and water amount is decreasing every year all over the world, so these technologies are become more common and their cost decreasing sharply. For example, in Turkey, and the water cost in the municipalities for the industries increase over the €2 per meter cube. So it is much higher compared to 10 years before. So I can say that the water cost for the industries may increase over 10 times in the municipalities. So now using membrane processes for wastewater recovery is become more and more common, because I can say that for the wastewater, for 1 meter cube, you are spending only €1 for 1 meter cube, but it is higher than €2 if you try to buy the water from municipalities. So as I have mentioned, the challenge is the high initial and operational cost of the membrane processes, but it seems that their cost decreasing because of their increasing usage and our experiences in the projecting these processes. So as I have mentioned, the membrane processes has very high efficiency in the pesticide removal and salinity removal, but the concentrate stream is the main problem, another main issue. So one of the main aim of the PIRMA project is also to deal with the concentrate, which includes high concentration of pesticide and salinity. So we have also used some membrane and bio-based technologies in order to decrease the risk in the concentrates. So that's what I can mention about membrane technologies.
Thank you, Eric. I fully agree. Thank you, Eric. I fully agree. The main challenge is the economical sustainability. But you're right. The cost is decreasing. So, if in view of time, if there is no further question, I think we can close the webinar. But before, I would like to thank again very much Erkan, Eric, and Francesco for the very nice presentations. And I would like to thank MDPI and Sustainability Journal for giving us this great opportunity to present our research project. And of course, I would like to thank all the participants to be here this morning with us, morning in Europe and afternoon in Asia. I can see we have many participants, more than 80 participants. So we are very happy with the success of this webinar. And we would like to organize another one, maybe at the end of the year, November, December. So we will discuss about this, and hopefully MDPI will support again us. And if this is possible, then we will advertise via the LinkedIn profile of the MedInCircle project. So for the participants, if you are interested, as I can see from the chart, you can just follow the project on LinkedIn, and we will give you the information for the next webinar. So thank you very much.
Thank you so much, Professor Giovanni. Thank you so much to all speakers today and all participants. Of course, MDPI will be pleased to organize such a webinar in the future. So we will stay in contact and hopefully have such a successful project in the future. So thank you so much all, and have a great rest of the day.
Thank you.
Thank you.
Thank you.
Thank you.
Goodbye.
Bye. Goodbye.
Bye.
Bye.